largest, the very smallest. I'm enthralled to cosmology. I'm a devotee of fundamental physics. In cosmology, the very largest, the universe is now said to contain 2 trillion galaxies. That's just the visible universe. And no one thinks that the universe stops at what we can see. In fundamental physics, the very smallest, we search for deep harmony of all particles and forces, and ultimate unification, a final theory of everything. How to discern the deep meaning of physics and cosmology. That's what philosophy is supposed to do. Why philosophy of physics and cosmology? I'm Robert Lawrence Kuhn, and Closer to Truth is my journey to find out. To discern the deep meaning of physics and cosmology, I go to Banff, Canada, for a conference of the Foundational Questions Institute, FQXI, a gathering of physicists and cosmologists who dare to look over the scientific horizon. We're in the Canadian Rocky Mountains, and with quantum theory on the agenda, I'm walking a rocky road. There are so many innovative thinkers here, I'm already frustrated I can't talk to them all. I begin with a philosopher of physics known for defending the many worlds interpretation of quantum theory, where all reality splits off into alternative future histories. David Wallace. David, as someone who was trained in science, but as a non-physicist, I've always been interested in the deep implications of physics and cosmology, and philosophy of physics and cosmology seems like a way to understand that. But a lot of my physicist friends say that philosophy is, at best, an interference with what they do in science. You are a philosopher of physics, so help me understand what this field is and why it's important.
Sure. What philosophy of physics is engaged with is very much understanding some of the more conceptual, less calculational aspects of physics. And in that sense, it's continuous with physics itself. And I found as a PhD student that the questions I was interested in physics ended up going so much more towards those conceptual questions that it ended up making more sense to call myself a philosopher.
For example, what
Sure.
were some of those questions?
So the sort of big 3 questions that have dominated the subject have been, how do we think about quantum mechanics? How do we think about space and time? How do we think about the emergence of laws and physics on higher scales from things on smaller scales? And all of those questions are questions that at one point you'd have said were pure philosophy and became parts of physics as we got better at science. But they left behind conceptual questions that physicists care about as well, but that some of the methods and practices of philosophy come to play on. And I'd say, this is particularly relevant for the FQXI conference we're at, that there's in recent years been a sort of 4th branch of that, philosophy of cosmology, which has drawn on all 3 of those, but has asked some distinctive questions of its own.
So what are some of those distinctive questions? Because those are the ones I've been interested in.
I think a lot of them are to do with the nature of science and the scientific method in a domain where the rules seem to have changed a lot, where it's really hard to get evidence, where our own place in the universe seems to be playing a role in how we make predictions, and where really sober physicists are starting to say, for a bunch of different reasons, that there are vast numbers of universes, most of them are lifeless, and we need to understand why we're in the one we're in.
So 4 categories, quantum mechanics, space-time, something that seems to me is emergence in the broadest sense of the term, and cosmology. Just describe each one of those in terms of some of the deep questions and how progress can be made. Because some physicists say that as soon as any progress can be made, it comes out of philosophy and goes into physics.
Yes. So in philosophy of quantum mechanics, the big question is the quantum measurement problem. Quantum mechanics seems to say crazy things, either that there are parallel universes we can't see, there are, but moving on. Or that the observer is playing some crucial role.
Your theology.
Put my cards on the table. Yeah, the observer is playing some crucial role, or that our fundamental theories are wrong and need changing.
Okay, those are three possibilities. Yep. Very good.
Philosophy of space-time, I'd say these days the most crucial questions are how do we continue to think about the nature of space and time in the context of quantum theories of gravity, where there's breaking up. Are they discrete?
Emergent.
Exactly. Is our fundamental theory something that's not describable in the language of space and time? Since every physics we've ever done is describable in the language of space and time, that kind of looks like a problem. Biggest question in the philosophy of, well, what you call philosophy of emergence, which I think is fine, but sometimes gets called philosophy of statistical mechanics. I'd say the biggest question is about the distinction between the past and the future. How come the microphysics we have, which doesn't seem to care, gives rise to a macrophysics that seems to care a lot?
So that's an arrow of time?
Exactly.
So arrow of time is a subset of this kind of emergent area of physics.
That's right, because what emerges has an arrow of time in, and what it emerges from, it seems, doesn't. And that seems almost like a contradiction.
Okay, wow. And then in philosophy of cosmology?
I kind of think we don't yet know what the biggest question is, but I'd say a good contender for first place is just how do we modify our scientific methodology to allow for the very different context of experiment and observation we find ourselves in cosmology. And this is a place, I think, where even hard-nosed physicists have found themselves having to be quite philosophical to say things about the observer and the mind that you wouldn't have managed to get published in serious physics journals even maybe 15 years ago.
And today can.
I mean, not that everyone's happy with that.
Right. Yeah. How do you see the development of the field?
I think the optimist in me thinks that what really matters is that philosophy of physics gets better than it is now at really engaging with and talking to physics and listening to what physics says back. Frankly, I think the field needs to up its game a bit.
In the philosophy of physics and cosmology, I hear four categories of questions. 1. How does quantum mechanics work? 2. What is space-time? 3. How does our ordinary macroscopic world, with all its complexity and normality, emerge from the fundamental microscopic world with all its simplicity and strangeness? 4. What counts for science in cosmology? Great questions probing the deep meaning of reality. I need to dig deeper. I start with the mystery of our ordinary world. How does complexity come from simplicity? I speak with a big picture physicist and cosmologist, author of, unsurprisingly, The Big Picture, on the origins of life, meaning in the universe, Sean Carroll. Sean, what's the philosophy of physics or cosmology? And one of the big questions is that in any start to the system, everything is extremely simple. And so the question is, how do you go from the extremely simple to what we have now, which is extremely complex, especially when you have the second law of thermodynamics pushing seemingly in the opposite direction?
Yeah, I mean, there's an old kind of silly question, right, which says, if you claim that the universe is just winding down, becoming more disorganized, entropy is increasing, the second law, then how in the world do you explain the coming into being without some transcendent purpose of these exquisitely organized systems like you and me? And of course, scientists have a cut and dried answer to that. The Earth and its biosphere is not a closed system. And in open systems, and ones that are interacting with their environments, entropy can go down. I can put a bottle of champagne in the refrigerator, cool it, its entropy will go down. And that's true, but it doesn't explain why it actually does happen. It says it's okay, it's allowed by the laws of physics for complex structures to come into existence here on Earth, but it doesn't say why it does. And I think the answer to that lies in the distinction between entropy, low entropy being orderly, high entropy being disorderly, and simplicity versus complexity. These are two very, very different things. I would argue that not only is it allowed that complex structures come into existence as the universe expands and entropy increases, But it is necessary for that process to happen in order to allow complexity to arise. It's definitely an interplay of the different forces. The fact that we have gravity, which only pulls things together, the nuclear force, which holds nuclei together, and electromagnetism, which kind of can push or pull, depending on the situation. All of these play together to allow the complexity to come into being. But it's temporary. The analogy I like to use is cream and coffee mixing together. When the cream and coffee are separate, that's a low entropy, organized system. It's also very, very simple. When they're all mixed together, it's high entropy, disorganized, but again, very, very simple. It's in between. When the tendrils of the cream and coffee are mixing into each other, that's when it's complex. It's the fact that entropy is increasing that lets this complexity come into being, at least for a little while, before it eventually fades away again.
And is that your metaphor for the entire universe?
The universe does exactly the same thing. The universe starts very simple, very organized and low entropy. It will end in the far future, billions and billions of years from now, simple again, because the universe is going to expand and cool and empty out. It'll be very high entropy, but once again simple. It's this in-between phase in the middle that you see complexity. You and I are those cream and coffee tendrils mixing into each other.
And this is the time that we can see other galaxies. They haven't flown away from each other. So does that make you wonder about this time and this oddity that the universe goes from utter simplicity to utter simplicity? And here we have this time. Isn't that a strange way for reality to be?
The fact that the universe started in such an extremely simple low entropy state is indeed very, very puzzling. This is one of the primary things that cosmologists spend their waking hours worrying about. The fact that given that we did that, complex structures come into being in the aftermath, and that's the era of the universe's history which we find ourselves, is the least surprising thing in the world. I mean, there's clearly a selection effect. We're very complicated. What's the universe going to look like when we wake up and look at it? It's going to be in the complicated
Right, but you're assuming the existence of those forces.
Yeah,
Of gravity and electromagnetism and strong force and weak force and quantum wave functions and all sorts of things.
You need a universe that is rich enough in its fundamental dynamics to have pushing and pulling on different scales. Right. Without both pushing and pulling, you're not going to get complex structures forming. In fact, we simulated cream and coffee mixing into each other, and we found that for some versions, they just sort of smoothly spread into each other and complexity never arose. For different quote-unquote laws of physics, they become very complicated. Physics, But, there wasn't a lot of fine-tuning involved. It wasn't hard to find versions of those laws where they became very intricate and complex.
But doesn't it strike you in some odd way that you have these very complicated things and quantum wave function and the four forces of nature, gravity, electromagnetism, we talked about them, and then going from simplicity back to simplicity. I mean, that's the way reality is.
That's right. That's the way reality is. And
doesn't that bother you?
No. It makes me curious. I'm wondering why it's like that versus some other way. I'm not sure whether there's a good answer to that. I have no idea how surprised we should be that the fundamental laws of physics seem to allow for enough complexity to give us not only intricate structures in the universe, but self-aware, information processing, future predicting substructures of the universe.
And then disappearing.
And then we'll go away. Yep.
And then disappearing. It seems like a cosmic joke.
Well, it certainly is absurd in the existentialist sense, right? There's no reason why it's like that as far as we know. Fortunately, that's what it is.
How complexity emerges from simplicity makes scientific sense. But then for complexity to devolve back into simplicity as the universe expands and dilutes into emptiness, and for such simplicity to remain static forever, I cannot help but wonder what an odd way for the universe to end. Explaining the odd ending or its alternatives, that's for philosophy. Another oddity is how the universe began, the origin of space and time, as well as matter and energy. I speak with physicist James Harden, who developed the Hartle-Hawking wave function of the universe. Before what we call the beginning, he proposes, there was no time, only space. the universe had no beginning. Jim, what are some of the most important contributional theories that together can give us an understanding of the meaning of cosmology?
What's important, right, is to understand our universe, how it evolved, right? What are the laws that govern the regularities that we see in it, right? From the point of view of fundamental physics. That means quantum gravity, and it means a theory of the quantum state of the universe. It means two pieces, right? A theory of the dynamics and a theory of the state, and then to see what we can predict from realistic theories and test them against what we see of the universe today. It's not really different from what human beings have been doing for thousands of years, trying to understand whatever the universe seems to them as a whole in terms of basic physical laws. We have a better appreciation today because we're able to do more experiments of the nature of those laws. It's a big extrapolation to apply them to the universe, but a necessary one to continue this tradition, and hopefully we'll be successful in discovering what theories really compress all the discussions of the regularities we see all over the universe and explain those that aren't the results of that, but are a result of quantum accidents like evolution that occurred over the course of its history. What can we explain, right, and how do we explain it?
So we deal with an initial state and then a process of a dynamic process to have that state go forward in time.
Except for the word initial, I'm with you on this, because there's no time, right? The world is four-dimensional, as far as we can tell, or 10-dimensional according to string theory, or more or less. So we need to understand not only evolution, that comes later, we need to understand the prerequisite for evolution, which is a classical spacetime. What classical spacetimes come out of a quantum universe?
Yeah. What are the importance of some of the areas that you focused on? The wave function of the universe, the Hartle-Hawking state. How do these big, interesting, original ideas affect that overall philosophy of state and dynamism?
They tell us that the evidence and the observations of the universe are that it was much simpler earlier than it is now. More homogeneous, more isotropic, more nearly in thermal equilibrium. The light from the Big Bang, right, shows very tiny fluctuations, the order of 1 part in 10,000 in the temperature. Yet those fluctuations were important because the collapse of those fluctuations gave rise to the stars, galaxies, and ultimately the biota and human beings that we see today. It's the standard effort, I think, of human society to try to put what we see in order. As Bohr said, the task of physics is to extend its range and reduce the phenomena to order. And that's exactly what we're doing in quantum cosmology. We're extending it to the biggest possible range, the whole thing, and we're trying to reduce it to order, right, that explains what we see today.
Trying to find my way amidst the astonishing reach of human knowledge, I remain transfixed. It's not just me. There's increasing public fascination with physics and cosmology. That's good for the support of science, but is there larger meaning? That only philosophy can provide. That's why I seek the author of 7 Brief Lessons in Physics, an expert in quantum gravity, Carlo Rovelli. Carlo, I like to talk about the philosophy of physics, the philosophy of cosmology, in order to see the broader implications of the scientific theory. Reflect for me the importance of communicating the essence of physics to large audiences.
People want to know what is happening in modern science, quantum gravity, cosmology, particle physics, quantum mechanics, general relativity, but also want to know the implications of that. Also, I think that's what is more meaningful and significant is in the science that we do. A conference like the conference here, it's not a technical conference about adding details to some information about physics. It's trying to go to the deep questions, to the core questions. What do we know about reality? What we don't know about time? What do we know about the observable, or what we know? And I think that the distance between physics and philosophy is small. It's very small. Physics nourish itself from philosophy. The best philosophy find nurture in physics. Why? Because our understanding of the world is one. It's not broken in pieces. We don't have a physics and a philosophical or religious. We are just unitary beings which try to bring together a vision of the world based on everything we know.
You've picked 7 ideas. So what are the 7? And why do they express fundamentally the philosophy of physics?
The first chapter is on general relativity, because it has changed in depth what we mean about space and time. The second is about quantum mechanics. Quantum mechanics has changed, and is still changing in depth what we think about matter. Matter is different from what we thought before. So it's the second
And
one.
is the fundamental basis for everything that exists, obviously.
Exactly. So, but quantum mechanics tell us that the world is not made by stones, by things. Yeah. So it's a new world.
It's a total. So both of the first 2 are different ways of thinking about things that we thought were obvious and self-evident, and they're
exactly.
Neither.
Third about cosmology, it's basically a chapter with pictures. We saw the world, the ground and the sky, and then the earth and the sky, and the earth going around the sun, and then the galaxy, and then thousands of galaxies, and all this, and then the story. So this immense expansion
the
of
scope of reality.
Scope of reality.
Okay.
And the smallness of ourselves in the universe we see. The universe is incredibly large. Then there's one chapter about quantum field theory.
Oh, okay.
Because quantum field theory, particle physics, quantum field theory is often presented in the form, there are this particle and this particle and these fields, but that's not the zoo. That's not the interesting part. That's a list of things. The interesting part is that particles are not really particles. I think that exist, don't exist. The vacuum is full of stuff. So there is this sort of vibration. The universe is like the universe of the hippies in the 60s, right? It's all vibrations, something like that. So again, it's sort of relativistic quantum mechanics, but it has changed our sense of what is stuff.
Okay. Yeah.
And up to now, it's mostly established physics. Then I go to quantum gravity, which is, I say clearly, it's a boundary. Now I tell you what we're trying to do. And I talk about quantum gravity, quantum granular space. I talk about loop quantum gravity, the structure of space and time, quantum structure of space and time. Then there's one chapter about heat and the relation between heat and time and gravity. Gravity changed time, changed the meaning of heat, black hole, all that. And there's the last lecture, which is not about physics really, but is about what are we in this funny world, the world of jumping particles, curved space, immense universe. What is human beings that feel, that know, that learn, that have understood all that? What are we? How can we think about that? And my own take is that we're part of this nature. And personally, emotionally, I find this immensely reassuring and calming. I'm home. I'm not in the natural world as an outsider. I'm in the natural world as part of it.
I admire your serenity, but I personally, after living through the 6 prior chapters, I'm agitated because I want to know what it all means. You are very calm to be subsumed in this very natural world and enjoy that, but people are different, and I'm agitated. I was calm before I heard your 6 chapters. Now I'm very agitated.
I'm sorry. It makes me more quiet by thinking that there are things I don't know. I have a partial understanding of reality, and that's it. I'm limited. I'm mortal. I think I'm going to die, and that's it. And this is an incredibly reassuring thing for me. I don't have to worry about eternity.
I'm stunned by infinity. I shudder before eternity. I marvel that we humans can comprehend endless time. It's part of the philosophy of physics and cosmology, a clear, if twisting, road to reality. The four big questions. 1. Quantum mechanics. 2. Space-time. 3. Our emergent world. 4. Cosmology. The puzzle of complexity from simplicity, and the relatively brief period when complexity exists. The vast size of the cosmos. We must never tire of this ultimate fact. Quantum gravity shaping cosmic structure and evolution, what any final theory must explain. The unity of knowledge, the deep truths when philosophy intersects physics and cosmology. On all this, I've two minds. One is awed by the beauty, the elegance of the science. The other is overwhelmed by the oddity, the strangeness of the reality. Perhaps both are closer to truth.
For complete interviews and for further information, please visit closertotruth.com.